All right, line 1, V1, learning task 3. It's our second video in the same learning task over here. The first video just covered off the first couple of circuits there, all the way up to figure 5, which was just going to be sequence control, and then on delay and off delay timing that we were going to look at. We're going to look at another timing one here, but it's less so about, creating a definite sequence and more so about preventing actual operational issues. And what we're going to look at now is we're going to start by taking a look at anti-plugging with time delay relays. We've talked about plug-in before, about what it actually is inside of a control circuit, and that's where we've got a motor that's operating in forward, and we want to go and put that thing into reverse. And so when we put it into reverse, it is going to go and have a phenomenal amount of torque that it has to go and overcome. Remember that motors develop current based upon the amount of torque. So there's a lot of momentum, there's going to be a lot of torque in that direction. It has to develop a counter current in the opposite direction. Really, what we have to do is we have to go from full RPM back down to 0 and all the way up to full RPM in the opposite direction. So instead of us having like a 300% inrush, if we're going to be plugging, we can be sitting up to like a 600% inrush. Not only is this hard on the motor, magnetically, the actual windings, the way that they get, stressed inside of there. It's also hard on our loads, on anything mechanical, belts, drives, pulleys, and stuff like that. So we want to be very careful about using this whole plugging thing, that we only do it when it's applicable. And if we've got a customer that wants to have something where they can operate it in forward and reverse, we want to go and question them as to whether or not they need to go and use reverse to stop the forward, etc. Because if they do, then it would be a plug-in type of circuit. If they don't, we want to prevent them from doing that, because it's just going to go and result in less damage overall to their systems. The way that we do that is we do that through this circuit over here, which is going to be referred to as an anti-plugging. In other words, it will not allow plugging type of circuit, and it's going to happen through the use of my time delay types of relays over here. Let's go and take a look at this thing running through here. First thing we're going to do is we're just going to go and carry power as far as power can get into this circuit, which is going to be that point over there. It's all the way up to the normally open push buttons, all the way up to the normally open contacts. If we go and press the forward button over here, as soon as we press the forward button, we could pass current through this normally closed reverse one. Reverse is not energized, therefore it's still normally closed. Through this, which is going to go and be, my slide just jumped around there, through this, which is going to go and be normally closed as well, right? If we take a look at this one here, it is a normally closed, time to close. We have not gone fired, TD2, because that's going to be over here. So it's not going to have changed in any state. And so we'll go and carry current all the way through to here. Forward will then go and turn on. I have no idea what's going on here right now. Forward will then go and turn on. Once forward turns on, then it is going to go and seal itself in over here like that. And at the same time as forward turns on, it is instantly going to go and operate this. Now you should be familiar with these symbols over here. These symbols are going to be normally closed, time to close, which means that at the instant of operation, they're going to go and, or at the instant of power, they're going to go and operate. So this one here is actually going to go and open up like that. And it's going to sit there and it has to go and wait at this point. So we're just going to stick a little bit of white out there and there. So we've got our circuit on the reverse side that is now going to be sitting open. Our motor would go and run in forward. We could run it in forward as long as we want. If we decided that we wanted to try and put it into reverse, I can press this reverse button all I want, and it will carry power through up to this TD1 contact. It will never make it through. So I'm not going to be able to go and stop the motor from running in forward by pressing reverse. It's anti-plugging, remember? If I do press stop, then it's going to go and interrupt. It's going to go and take out all of my energized components. It's going to go and take out this forward coil. It's going to go and take out this contact over here as well. And what's going to happen then is this timer, when it loses power, is going to start its timing. So it's going to go and start its timing, and it's going to wait 8 seconds before this recloses. How's this good for us? Well, really, it's going to be off the fact that if I stop this thing when it's running in forward, I can't hit stop and then immediately hit reverse, because for the first 8 seconds after I stop the motor, reverse does nothing. It only carries power up to this point over here. It cannot go any further into the circuit. And then when this thing has finished its timing, because we had been running it forward before, when it finishes its timing, it is then going to go and reset this, drop it back down to where it was. And at that point, me pressing the reverse button is now going to allow me to go and pick up and run this thing in reverse. And once again, it is going to go and open its associated winding up top over here, or its associated contact up top over here. This is just going to go and provide us with anti-plugging. off of these, so that it's going to be impossible for me to go and run that motor in reverse anytime that it's already been running forward, even if it's just coasting. It's easier in a lot of ways than to go and use a zero speed switch, because zero speed switch needs to be directly coupled onto whatever my motor is going to be. And it requires a lot of mechanical, stuff that's going to be part of it. We're not millwrights, we're electricians, so we prefer to do things in an electrical manner, which means that probably this is going to be my preferred method. The only problem that you're going to go and have with this is you need to time this thing, and you need to make sure that the customer's not going to be able to go and adjust that time. You want to go and start this thing, and you want to hit stop, and you want to be counting, 1 Mississippi, 2 Mississippi, etc., until you can go and figure out how long it's going to take for that thing to spool down and forward. You're going to spool it down and reverse, and then you're going to, if there's load, hopefully run it loaded and make sure that that is not going to cause it to, overrun that time. You got to time that thing, and away you go. Now, going back to what we've talked about so many times with our electronic timers, the electronic coil timers are not going to go and be used anymore, right? We're not using the electronic timer coils anymore, the pneumatic and hydraulic ones, because they are bulky, expensive, and a pain. We're going to go and use electronic ones. In an electronic type of circuit, what we would need to go and do is we would need to go and run just a separate run over here. We're going to go and run a separate run that is just going to be constant power to my timers. TD1 coil. I'm not going to say it like that. I'm going to take that one all the way back over here, as well as to my TD2 coil. Okay, we're just going to go and run those two with constant power. They're small, they're just electronic. They just need to go and run in the background. All this is doing is just making sure that they're awake and they're ready. What we then do is we are going to go and lose this coil operation inside of here. We're no longer going to have that coil. We're no longer going to go and have this coil over here. And all that we are going to do in their place is we are going to go and take them into an input on this, right? This one's going to go into a TD1 input. This one over here is going to go into a TD2 input. TD2, TD1 that we are going to go and have keeps doing that thing where the whiteout goes over top of it. But you get what I'm saying. We're just going to bring them into an input. Inputs are really hard to visualize for the first bit until you get around to actually using them, because we don't see anything that, completes that path. We're so, glued into this whole, we got to have a completed path, etc., back and forth. With an input, we're not worrying about having a completed path. It's just an input that's going to go and exist. For the rest, my operation would stay the same. Once I go and get that input onto here, everything else just stays the same. It's still going to go and have a normally closed time to close contact that we are going to go and utilize up top here. They don't actually look like this. Everybody knows that they just look like screw terminals on the timers. But yeah, this is how we would go and accomplish this using my digital timers. Okay, let's go and talk about pump controls. Oh, sorry, this is the wiring diagram that they had for that one. This is the wiring diagram that they had using those old pneumatic and hydraulics. Because we don't use a lot of the old pneumatic and hydraulics, I'm not going to go through this one, because redrawing it to the digital electronic ones is just, it's going to get too crowded and complicated inside here. Just suffice it to say, we're not using those other timers anymore. We're going to go and have the electronics. Let's talk about this one over here for pumps for movement of water. Movement of water, particularly when we are moving water from some place where it is low and we are pushing that water up, is going to go and cause a little bit of a problem sometimes, because it's a dynamic type of thing. It's not like a really physical load. Everybody knows water is like gushy and soft. So whenever we are pushing water, we are going to go and get a little bit of dynamic feedback that is going to go and happen. Usually when we are pumping, if we have got an actual pump, we'll just draw a pump over here. That looks like a G for some reason. Let me just think, how do I draw a pump again? Oh yeah, we'll just draw like that. Okay, so we got our little impeller that is going to be pushing all of that water through my pump here. So I'm going to go and pick up water. I'm going to go and drive it through here and up and out. Usually what we're going to have is we're going to go and have a check valve. And a check valve is just simply going to be something where stuff can go through in one direction, but it's not going to be able to go back in the other. Now, normally when I'm pumping up like this, I'm going to go and have water that's going to be flowing. But as soon as I would shut this pump off, all that water it bounces. It kind of has this like bounce type of thing that happens because it's a dynamic, gushy type of thing. It is going to go and cause chatter, because what happens is it was pushing up. And imagine throwing a ball up into the air, right? You throw a ball up into the air, it kind of hits an equinox when it loses all of the force that's behind it, and then it falls back. We're getting the same thing with the water. We've shut the pump off. We're no longer pushing it up, so it's going to start to go and fall back. It's going to fall back. It's going to compress, and then it's going to bounce up a little bit. It's going to bounce down, etc. And so we get this thing that's very much like a basketball being dropped. It's going to kind of turn down like that. What happens, though, is we're going to get these spikes, these pressure spikes. And if we've got a pressure switch inside of there, that pressure switch could get triggered artificially on a couple of these spikes, because those spikes that bounce the water column will be enough to go and drive them in there. What we will do in those cases is we are going to go and put a delay onto our activation. Really, that's all that we are doing with these, is we are going to go and delay our inputs. We're going to see the same thing that we're going to happen inside of a lot of our electronics, the PLCs and things like that, where we're going to be able to go and choose how long a signal has to be there before we actually say it's a valid signal. Because anything that's too short is going to go and be, considered to just be what we call bounce. It's technically called debouncing. Waiting for a signal to stabilize that's what the term is. They talk about contact chatter. Contact chatter is just the fact that doom, 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 I'm getting this, back and forth. That's going to go and happen. The other issue that you can have with these as well is that if you have got pumps that are pushing up that don't have a check valve, then you are going to go and have water that is then going to push backwards down. It's going to fall. Gravity pulls it back down. It's going to spin the motor backwards. And if we try to run the motor at that point, it would basically be plugging, right? Because the water is shoving it backwards, but we're trying to start it forward. It would be bad for it. So we have these based on those physical circumstances. We're going to go and have these controls that we are going to have over here. The simple definition for this is that this needs to be held. Whatever my control is going to be, whether it's going to be a start push button or a pump switch, it just needs to be held for 3 seconds. As long as we do that, for 3 seconds. As long as we do that, we know that we have stabilized. That this thing, it's not just seeing a little bounce spike that we're seeing a pressure over there. We know that it's an actual called for thing. If I'm looking at a pressure switch here. So we've got inside of here, we'll just examine just the auto right now. We'll put the selector switch. This is a handoff auto switch. If I move that auto switch into here, what I would see is that as my pressure goes up, that I'm then going to go and turn this relay on. So once my pressure goes up consistently, not bounce. If it bounces, it's going to hit this on delay, and the on delay is going to start timing. Let's say the timer is timing for 5 seconds. Well, we said 3 seconds, so we should maybe go with that. So since it is 3 seconds, let's work with the 3 seconds over here. Basically, what we need to have is we need to go and have this thing time for 3 seconds. So if we get a little bounce, a little bit of contact chatter, it's going to start timing 1/1000 up, and then all of a sudden, the bounce disappears. And so then it resets the timer. And the next bounce comes in, and it waits, and it tries to. And as long as those bounces are each going to be less than 3 seconds in duration, it's never going to be able to go and pass that signal all the way through to the next rung over here. If it is a consistent rise in pressure, we actually have, a rise in pressure that requires us to start pumping. At that point, that consistent rise in pressure, an actual rise in pressure, would just be a linear type of thing that we would see, and it would get above that, threshold that it needs, and it would stay above there for at least 3 seconds. And at that point, this thing would be able to start up, because the second that we get to pressure, this thing starts timing 1/1000, 2/1000, 3/1000, and if the pressure is steady, it will then go and close this one here, right? It's a normally open time to close, which would then go and start up my actual motor on here. This just goes and prevents us from having any just chatter or the pump that's hammering on, hammering off, etc. This one does not go and change a lot of my operation when it comes to any backspin, though. They do talk about backspin where I've got that column of water proceeding back down the well shaft. If that would go and happen, backspin would need to go and have some sort of a timing that would go and happen on there to prevent it. We'd have to go with anti-plugging, more similar to what we saw with the other one, where we would need to go and have an off delay placed in line with this one as well. Well, actually, I guess when you look at it, it does provide 3 seconds of, anti-backspin, because it won't be able to start for at least 3 seconds until we restart it anyways. If we do shut it off, it does have to go and start for 3 seconds. So I guess maybe, there is a limited amount of backspin, but usually that's going to be done more with an off delay that is going to go and wait to reapply power to my actual startup system. The hand position that we do have inside of here is just there for us to be able to manually override, if we need to go and turn this thing on. A lot of pumping systems usually aren't danger critical type of systems. And so in a lot of pumping systems, we want to go and have it on because if we're not quite at the point where we need to start pumping, but maybe we're getting close or it's the end of the day, we want to clean up some pits or something like that, usually then we'll want to go and start them up and actually run them. Okay, let's take a look at some limit switches. And let's take a look at how they are placed into safeties for a garage door over here. Now, this is not really a technical garage door the way that most of us are seeing. This is more for an automatic door. They talk about semi-automatic control of a door. Really what they're meaning is that somebody's going to be able to come up, they're going to go and press the open button, and their door is going to go and open. So press the button, which is going to go and cause the door to go and open. And then once the door gets all the way open, then the door is going to start waiting. And once it finishes waiting, then it is going to go and close again. So that's what the type of control that they're trying to go and have over here. You'll note that there's no door closed. There's just a door open. And it could be for a vertical overhead door. It could be for one of those sliding man doors where you walk up to that thing. When you enter into any type of a building, there's a little sensor instead of a button. There's just going to be an infrared sensor that is going to sense that you're there. It's going to go open the door is going to hold open. And then once it just kind of starts timing, and then it shuts back down again. That's what we're looking at over here. We've got two sets of limit switches that are going to be on here. We are going to go and have one limit switch over here. We're going to call that one the nacho switch. It's not actually, it's normally closed, held open. I just think it looks like nachos, and now I'm getting hungry sitting here in the garage. But this one is going to be based off of the lower or the closed position. We're going to have this one here that is going to be based off of my upper or my open position. I'm going to go and label these things as being closed, and I'm going to label these as being off the open position that we are going to go and have. These two are tied together, meaning that as soon as we bump this thing, this one would go and close, this one would simultaneously go and open. So that's the positions that they're tied to over here. Here's what happens when somebody walks it up to the door and presses it. First, we're going to start by highlighting where we have got power up to. We've got power up to here, and up to here at this point. That's as far as power can proceed down this circuit. As soon as somebody comes in and presses the door up button, that door up button is going to go and provide power through here. Now remember that these limit switches are not toggled till we hit the top of the door. So these ones here are going to be closed right now. So we are going to go and provide power to my up, which is going to go and start running my door all the way up. So the door is going to go and run all the way up to the top. Once it gets all the way up to the top, then we're going to get something else that's going to happen. Let's start by just making a little diagram over here right now to just show our door. We're just going to have LS1 for this one and LS2 for that one there, which is going to be my lower limit switch, my upper limit switch. So we press the button, the door is then going to start rising up. At the same time as the door starts rising up, it instantaneously is going to go and energize this timing relay. Is it on delay or off delay? Well, I don't know. I'm going to have to take a look at the contacts. When I take a look at the contacts, I see that it is a normally closed time to close, which means that instantly, as soon as I powered that up, this thing here would have, boom, kicked all the way open right now. Okay? So our door is rising. The instant that we provided power, this timer opened up over here. It's going to go and stay open right now. The door rises, and eventually that door is going to get all the way up to the top where it's going to go and hit limit switch 1. And it's going to go and open this over here, while simultaneously it is going to go and close this over here. When it goes and closes this, when it hits that top switch there and opens, it is going to go and take out this control circuit here. It's going to take out that timer, and because this is a time delay timer, that means that this thing is now going to start its timing sequence. In the meantime, I should have mentioned this one here. When the door started lifting, I should have mentioned that before, but when the door started lifting up, as soon as it lifted up off that bottom switch, this one here would have been closed. So this one is closed right now. So the door made it all the way to the top where it hit that limit switch, kicked out the rising, the upping contact over here. Starting to time, we've got power that is now going to be carried through here, all the way through here, because it's sitting up against that limit switch, closing that one. And it's going to go all the way through up to here, but that's as far as our power is going to go, because we're still waiting for this timer. When this timer finishes its timing sequence, boom, it is then going to go and close and as it closes, that is now going to allow power to proceed all the way to my down, which means that the down is going to go and seal in right over here, and my door is going to start to go and proceed back in the opposite direction. It's going to start going down out of here. As that door goes down, it is going to move away from the top limit switch, which is going to go and reclose that and open this one. But that's okay because we have got this sealed in over here. It is going to go and continue going down until it hits the very bottom. Once it hits the very bottom of the door over here, it's going to hit limit switch 2, which is going to open that up, and it's going to go and shut this thing back down. The door is going to be primed and ready to go and start once again. Lovely. It's a easy one. This is very common in industry that we're going to have door openers. So, especially in areas like warehousing and things like that where people are often carrying stuff, we're going to want to kick this thing, with a little foot pad or something like that, and the door opens and somebody can go and roll on through. Okay. Now we are on to our very last one, which is going to be our wood chip conveyor over here. And the wood chip conveyor has got a ton of control. We're going to once again stop the series here and I'm going to go and start a new one for the last one.